Welcome to the UGC lecture series. In this lecture, we are going to talk about binary search trees and the deletion of nodes from a binary search tree. This is a very challenging procedure because we have to, as you remember, when we change the binary search tree by deleting nodes from it or inserting, we need to still maintain the binary search property, the property of a binary search tree, and that is why this deletion becomes a challenging task. Now, let us look at what we mean by this. So, the objectives of this lecture is to talk to you about the deletion of nodes from a binary search tree, and there are three cases that we are going to consider, and we are going to look at each of the three cases in detail and see how deletion is done for these three cases. So, we are basically going to talk about removing or deleting a node from a binary search tree. There are three cases as I told you. Let me first explain the concept behind the three cases. Now, if the node to be deleted is a terminal node, then the deletion is a straightforward procedure. It is like you just delete the node. Now, this is like saying that if the node has no other descendants or has no children, then there is no problem, you can just delete it from the picture. If the node being deleted has one child, then that is, it has either a left subtree or a right subtree, only one of them, then what you do is you delete the node and attach the child to the parent of the node that has been deleted. That is the second case. This is also fairly straightforward. Only thing is you have to find the node to be deleted and you have to keep track of the address of the parent. That is the only complication. The third case is the most interesting case. What we are doing here is the node to be deleted has both children, that is, has got a left subtree and a right subtree. In this case, what we do is we have a sub procedure where we find the in order successor of the node to be deleted and replace the node that has to be deleted by this in order successor. So, how do we get the in order successor? The in order successor of a node can be obtained by taking the right node of the current node and traversing to the left till we reach the leftmost node. So, that is considered as the in order successor of a node. So, that is a separate procedure. You call this procedure only in the third case where the node that you want to delete has both left and right children or subtrees. So, in this lecture we are going to look at each of these cases in detail. So, what do you mean by removal or deletion? It removes a specified item from the binary search tree. The problem here is we want to adjust the tree. So, first we use the binary search, which we also used in insertion, to locate the target item. For this we start with the root node and it probes down the tree till you find the target or you reach a leaf node or a terminal node, which tells me that this node that you said you have to delete is not in the tree at all. So, that is an error condition, and then when you remove a node, you will leave a gap in the tree. It is up to you to fill up the gap. If you take this node, because of deletion of one particular node there, which has been shown as this node, there is a gap. Now, you have to fill this gap. How do you fill this gap is the question that we have to answer. I will just explain to you this particular example. Now, what happens? There is a gap here, we have deleted it. So, you have to find the in order successor of this node, fairly simple. The successor of this node is this. So, you take this node and replace it there. When you replace it there, 0160039 comes here. This is less than that. So, the binary search property holds good. I am just explaining a very simple case for you. Please note we are talking about binary search tree. So, let us take the case 1. If the node to be deleted is not the root, if the node to be deleted is not the root. Now, there is a slight emphasis here of whether the node to be deleted is the root or not, because the root is the access point to the outside of the outside world, and so if the root is deleted we have to make certain corrections there, that is why. So, if the node to be deleted is not the root, then it is fairly easy. Delete the node from the left or right subtree and replace the subtree. So, what you do is, suppose this is the node you want to delete is in the left subtree, then what you do is you will delete it from the left subtree, do the adjustment here, keep doing this till you reach the you have completed the recursive procedure. Now, if the node to be deleted is the root and the root has no children, then you just return the empty subtree, empty binary search tree, and that is it. The third case is if the node to be deleted is the root and the root has only one child, then it is easy, you just remove the root and replace this as the root. Now, if the node to be deleted is the root and the root has 2 children, then find the node with the smallest key in the right subtree, and use that as the root. Replace that here. This is the third case. Let us now try to develop. I have explained the process for you. Again I will repeat. First case is there are the node that you want to delete is a terminal node, just delete it. If it has one child, then what you do is you attach the child that is there, the node to be deleted has one child, you attach the child to the parent of the node that has to be deleted. That is the second case. The third case is that the node has 2 children, then you have to find the in-order successor of the node to be deleted and replace the node to be deleted by the in-order successor. For doing that, whatever you have to do has to be done. Please note that the in-order successor has a property that the in-order successor will have only one child. Either it will have no children or it will have only one child. Now, please think about that, because the in-order, by definition of in-order successor, the in-order successor node will not have a left child. If it has a left child, that left child would have been the in-order successor. So, that property is there for in-order successor. So, let us look at the pseudocode. If the tree is empty, then return false. Obviously, from an empty tree you cannot delete a node. Then attempt to locate the node containing the target using the binary search algorithm. This we have explained in detail in the last lecture where we spoke about insertion. For insertion also you have to find the location of the node. Now, if it is not found, that is the node you want to delete is not found, then it is an error. So, you mark it as error. If the node has been found, we have to remove it. Again, as I told you, we have 3 cases. If the node that you want to remove has 2 empty subtrees, replace the link in the parent with null. So, initially it would have been pointing to this node, make it null. We are going little bit more in detail. If the node has a left and a right subtree, replace the node's value with the maximum value in the left subtree, delete the maximum node in the left subtree. Case 3, if the node has no left child, link the parent of the node to the right subtree. If the node has no right child, link the parent of the target to the left subtree, and so on. Here this is the toughest case. If the node has a left and right subtree, replace the node's value with the maximum value in the left subtree. If it is the maximum value in the left subtree, then it is not the in-order successor, it is the in-order predecessor. So, you can do it both ways. This pseudocode talks about in-order predecessor, and now you are left with deleting that node. So, that is the pseudocode. So, let us take this case, removing a node with 2 empty subtrees, that is the easiest case. So, I want to remove 4. So, 4 has 2, it is a terminal node. So, both it has no children, has an empty left subtree, has an empty right subtree. So, what you do is you just have to, this is the parent node, you always have to keep track of the parent node. So, the link of the parent node would have been pointing to this node, it would have had a value, now you replace it with null. So, replace a link in the parent with null. So, that way this node has been deleted. So, this is the new tree after the deletion of 4. Remove a node with 2 subtrees, replace the node's value with the maximum value in the left subtree, delete the maximum node in the left subtree. So, now suppose I want to remove 7. There are 2 ways on doing this. This is the in-order predecessor. You can do it with in-order predecessor or you can do it with in-order successor. Let us first look at in-order predecessor, both are correct. So, now suppose you have 7, now it has both the left subtree and the right subtree. Okay. Now, before you start the algorithm, you have to find the in-order predecessor of 7. Now, in-order predecessor of 7 is the maximum, this left subtree, in the left subtree the maximum value is the in-order predecessor. So, this is the in-order predecessor of 7. So, please note, I hope you know what you mean by in-order. It is in-order predecessor or in-order successor. You can use both for this deletion algorithm. It means that if you traverse the tree in order, for this node, what is the immediately preceding node is called the in-order predecessor, and the immediately succeeding node is called the in-order successor. So, what we have found here is 6 is the in-order predecessor. Now, you have to replace 7 with 6. But for doing that you have to delete 6. Now, for deletion 6 you have come back to case 1 where the node has no children. In this case it has no children. So, if it has no children, what you do, you just delete this node, makes this node's parent point to null now, and this 6 comes here So, this value has been replaced by 6 and 7 has been removed. Here 6 has been replaced, and if you look, this is the modified tree, the binary search property holds good. Now, the question asked is what are the element can be used as replacement. Now, let us take the same example. You can use the in order successor also as a replacement. Now, what is the in order successor of 7? In this case, the in order successor of 7 is 8, that is the least value in the right subtree. It is the least or the minimum value in the right subtree. So, you take 8, delete 8, that means make the child of 9 equal to null and replace 8 here. Still the property holds good. So, both can be done. The third case is removing a node. This is simple compared to the second case. Removing a node which has one empty subtree, assuming that you want to remove 5. Now, 5 has no left child. So, what you have to do is you have to link the parent of the node you want to delete, that is 7 to 6. So, now what happens? Initially it was like this. Now, you are making 7's left pointer which was pointing to 5. Now, 7's left pointer is going to point to the right pointer of 5. So, that is what you have, and this is the new tree. Now, if you can also have a case where you want to delete 5 when it has no right subtree. In that case also what you do, you make the parent which is 7 point to 4. That means the left pointer of 7 will point to the left pointer of 5 and 5 will be removed. So, what was previously like this would now be replaced like this. This is the new. So, we have seen all the cases. So, for deletion there are 3 cases. One subtree, whether it is left or right, one subtree is alone is considered as a single case in some ways. So, if the element is a leaf, then or the element is a degree 1 node, that is it has one child, exactly one empty subtree, or it has a element is a degree 2 node, that it has exactly 2 non-empty subtrees. So, let us take again an example to just emphasize what we are trying to say. For case 1, we can simply discard the leaf node. Example, you want to delete 7, just discard it, that is it. So, discard the node. So, suppose you want to delete 35, again you can just discard it. Delete from a degree 1 node. So, degree 1 node example, so which node has degree 1 here? 30 has degree 1, 15 has degree 1, any other node? 40 has degree 1, 10 has degree 1. Okay. So, these are the nodes that have degree 1. So, example, suppose you want to delete 40, what you do is you make the parent of 40 to point to whichever child exists, in this case left child. So, make 20 point to 30. So, 40 has been removed. This is a very simple case and that link has been removed. So, delete again another example, suppose you want to delete 15, you just make the parent of 15 point to the child. So, that link has been removed. So, up to now we have seen how to delete the concept of deleting nodes from a binary search tree, and we have seen in an example of deleting nodes with degree 0 and nodes with degree 1. Now, we are looking at a node which has both the children. Okay. So, let us look at this tree. Now, which is the nodes that have degree 2? 20 has degree 2, 10 has degree 2, 6 has degree 2. So, these are the 3 nodes that if you want to delete, you have to follow this case. Now, suppose we want to delete 10. Okay. So, what we do is that is the node we want to delete. So, what we have to do is we have to replace 10 with the largest key in the left subtree, largest key in the left subtree, that is we want to find the in order predecessor. Now, the left subtree is this, the largest node in the left subtree is the in order predecessor, that is 8 is the in order predecessor of 10. So, 8 is the largest key in the left subtree. Now, you replace that there. Okay. Now, the issue here is when you are replacing this 8 here, this node is removed from the tree, this key is put here, key is put, the node is not removed, you are replacing this with this, and this 8 is removed from the tree. So, you are again you are left with a deletion, again a deletion. This deletion is done in such a way that I mean the property of in order predecessor is that this will necessarily have only a one child. So, for a one child, what you have to do, this parent of 8 has to now point to 7. Okay. So now parent of 6 has to point to 7 and that link has been removed and the 8, as you note, the 8 has been replaced here. So, this is the deletion after the so 10 has been replaced by 8, 8 has been removed from here and 6 is now pointing to 7. This is a new tree, and if you see, this tree follows the binary search property. So, note that the node with the largest key in the left subtree is guaranteed to be a node which has either 0 subtree or an 0 degree or a node with only 1 degree. It cannot be a degree 2 node. So, how do we find this largest key? So, by moving to the root of that subtree and then following a sequence of right child pointers until we reach a node whose right child pointer is null, that will be the maximum value. Let us just now you can do this, as I already told you, you can also do the same algorithm with in-order successor. For that you have to find the smallest key in the right subtree. There what we do, we move to the root of that subtree and then follow a left child pointer until we reach a node which has left child pointer to be null. So, this is to find the in-order predecessor and this is to find the in-order successor of any node. You can use either one of this to replace the node that has to be deleted, and the in-order successor or in-order predecessor will be removed from the tree, and because it has replaced the node to be deleted. Now, that in-order successor or the in-order predecessor that we have found will necessarily have only a one degree of it will be a node of degree 1. Suppose we want to delete the node root itself. Okay, this is an interesting example. So, if you want to delete the node root itself, we have to find, as we are taking the in-order predecessor, we have to find the largest node in the left subtree. Now, please note what was it to find, I will just go back. In order to find the largest key in the left subtree, you move to the root of that subtree and then follow a sequence of right child pointers until we reach a node whose right child pointer is null. So, let us go to that. So, this is the left subtree for which you want to find the largest. So, you keep on moving to the right subtree till you reach a point where the right pointer is null. So, this is the place where the right pointer is null, because that is the property you are searching for. Obviously, this node does not have a right pointer. So, which means the degree cannot be 2, it can be only 1 or 0. In this case, it so happens that the degree is 0. So, 18 is the in-order predecessor of 20. Then what you do, that we have found. Now, you replace this 18 here. So, that is what you do, and you have to remove this link. Okay. So, that is it, you just remove this link, and as far as that is concerned, that is it. Now, let us take another example. So, this is your result of the deletion, and the time complexity of this is 0 height, how much, basically to find the node. If you look at this delete 25, this is a simple case, you just delete it and this is the answer. Now, delete 10. So, you replace, so this is your, okay. So, you replace this 10 with the largest value in the left subtree. So, the largest value in the left subtree is 5. So, you replace 5 there and you have to remove 5. So, for removing 5, what you have to do, you have to connect 2 to the parent. So, that 2 is connected. Actually, this whole thing is moving up and then you delete the leaf. So, replacing 10 with the smallest value in the right subtree, that also you can do. So, suppose you want to replace this 10 with the smallest value, the in-order successor case, then the smallest value in the right subtree is 4. So, what you do is you replace smallest value in the right subtree. So, you replace it and the resulting tree is as it. So, now let us take the tree delete algorithm. If x has no children, it is a case of 0, then just remove x. If the x has one child, then it is case 1, that is node with degree 1, then make the parent of x to point to the child that x is. If x, the node to be deleted, has 2 children, 2 subtrees, then swap x with its successor or predecessor, in-order successor or predecessor, and this will result in the successor or the predecessor to be removed, and that will follow case 0 or case 1. and it takes approximately 0 h time to delete a node, which is the height, where h is the height of the tree. So, let us look at the pseudocode here. Determine which node to splice out, either z or z's successor. If left of z is null or right of z is null, okay, then y is equal to z and y is equal to tree successor of z. Now, set x to be a non-nil child of x or to nil if y has no children. If left y is equal to null, then x is equal to left of y, else x is equal to right of y. So, that is the algorithm for this. X is actually what? X is the non-nil child of x, that is what you have set it to be. So, now that x is made to point, left of y is made to point to that. If y is removed from the tree by manipulating pointers of py by px, this is the steps. Now, if parent of y is equal to null, then root of t is equal to x, that is if you are removing the root itself. Now, the other is that you are going to try to do the case 3 where you have to find the in order successor, that is this point. So, how do we check the correctness of tree deletion? How we did know that case 2 should go to case 0 or case 1 instead of back to case 2? That is what we are trying to say is case 0 in this case is when it has degree 0, node to be deleted as degree 0, case 1 is when it has degree 1 and case 2 is when it has degree 2. Now, when we are looking at successor, as I already told you, by the definition of in order predecessor will not have any right child, because if it has the right child, that right child would have been the predecessor. If it is the in order successor, that particular in order successor will not have any left child, because if that had been the left child, that would have been the least value. So, that way we are ensuring that we will never go back to case 2, we will go back to case 0 or case 1 and the successor node can easily be deleted. So, you can swap either the in order predecessor or the in order successor. You can try to do this if you have a lopsided tree. So, let us look at the analysis. Now, the complexity of the operations are get, which is basically search, insert and remove is all the three are of the order of h, where h is the height, and it will become log n if the tree is balanced. This we have not yet looked at. The updating operation causes the tree to become unbalanced. Tree can degenerate to a linear shape and the operations can also become 0n. So, the best case tree insert E, C, D, A, H, F. So, so you have a tree with E, C, then D comes to the right and A comes to the left, H is greater than E, so it goes here. Then you have F greater but less than H and K. So, this is the order in which this is a different representation. This is also sometimes used to represent a tree. This is the best case, because why is it called the best case? Because the tree is a complete full binary tree. So, any search algorithms, the number compared to the number of nodes, the height that you have to search for will be the least. This is the worst case. This is a skewed order. You just put it as 8, 7, 6, 5, 4, 3, 2, 1, it will come like this 8, 7 is less than 8, so here 6 is less than 7 and so on. So, this is a skewed order, and for just 8 nodes the height of the tree is 1, 2, 3, 4, 5, 6, 7. So, the height of the tree is 7. So, this is the worst case scenario. So, the random case it could be this way or that way. So, depending on that you have to do. So, what are the applications of binary search tree? You can sort with binary search tree. The input can be an unsorted array and the output can be a sorted array. How will it be a sorted array? If you do an in order traversal of the tree, it becomes a sorted array. So, the algorithm for this is basically you have an unsorted, build a binary search tree and then do an in order traversal. So, and you can use the binary search tree, and in order to avoid degeneration you can have a balanced conditions. So, that we will see later. So, the types of search tree which maintain the optimal balance, there are splay trees, AVL trees, 2-4 trees, red black trees and B trees. We are not going to go into all these details, we will take one of this and discuss it later. So, all these trees are some type of balance trees. Depending on what they say is the balance, the type of tree varies. The idea here is that if you want to get an optimal performance with, you already saw the worst case and the best case. So, if you want to get an optimal performance, you must see that the height of the tree is maintained, because as you saw the time taken for the algorithm is the order of h. So, if the H varies too much, then your time of doing all the operations becomes much higher. So, what we have done in this lecture is we have tried to understand the different cases for deletion from a binary search tree. We have also, so a binary search tree basically you have to search for the node you want to delete, you have to look at which are the 3 cases it belongs to. If it cases belong to 0 and 1, it is fairly straightforward and simple. If it is case 2 where the node to be deleted has 2 children, in that case we have to also call a separate algorithm called the in-order successor, maybe try to find the in-order successor and then do the deletion operation. So, the deletion of a leaf, deletion of a node with 1 child or node with 2 children are what is attempted in this lecture, and we are but obviously whatever deletion we do, we still have to maintain the binary search tree property. So, now let us look at given a binary search tree, I have given you a binary search tree and I want you to delete the following nodes, and you have to clearly state whether it is the degree of which case it belongs to or what degree of the node, and then you have to tell me the steps involved. So, first is we are trying to delete 35, then we are trying to delete 30 from the above tree, and then we are trying to delete 65 from the above tree. So, please try to do this. When you do this, you will see that we are tackling all the 3 cases, and what are the steps involved in the 3 cases you will be able to understand. When you are deleting 65, okay, try to do both replacement by in-order successor as well as replacement by in-order predecessor. So, in this lecture we have covered the basic deletion from a binary search tree. Thank you very much.